The greatest common factor. I often think of the greatest common factor as the golden rule of factoring. On this problem, we will assume the directions say factor completely. If I look at this and I'm trying to identify the greatest common factor, which you have to do first in all problems, I can see that it is 2xy. The reason being 2 is the greatest common factor of 8, negative 4, and 2. X is the greatest common factor of x squared, x cubed, and x. And y is the greatest common factor of y to the fifth, and y. Now to factor it, you have to multiply it times what would be left. What's left in this would end up being 2 times what gives you 8, which is a 4. X times what gives you x squared, which is an x. And y times what gives you y, it's just a 1. We took that y out, it's gone. The next term, 2 times negative 2, would give you negative 4. X times x to the second will give you x cubed, and y times y to the fourth is going to give you y to the fifth. In the last term, a common mistake is to say, well, I took it all out, there's nothing left. Be really careful of this. I notice that when I take it all out, I have to put the plus 1 because 1 times anything is itself. If you did not do that, if you multiplied it back to do the check, which is definitely suggested for any factoring problem to make sure you have it correct, you would be missing that last term. So make sure that you always check your answers or that you're really confident you have it correct. Factoring 4-term polynomials. The first step, as in any factoring problem, is to look for a GCF. Since there is no GCF in this problem, our next step will be to factor by grouping. This will require us to group our terms into pairs and take out a GCF of each pairing. And I'm left with A times C minus D in the front and a GCF of a B in the back terms. I'm left with C minus D. Now we will notice that we have a common binomial factor. Factor that out the same way you would factor out a monomial factor, and we're left with a C minus D times A plus B. You can always check your answer, as in any factoring problem, by multiplying back through and combining like terms, and you should end up with the original question. Factoring 3-term polynomials. There are 2 different types of 3-term polynomials or trinomials that we will look at. The first type is one like this one, where the leading coefficient of our, or A, which we'll call it, is 1. Why I call it A is because it is in the standard form ax squared plus bx plus c. And since A is 1, I'm actually going to show you an additional method that you can use to solve these, which I call the quick way, which I suggest. I think it's just much easier. Now, I am going to show you how to solve any 3-term polynomials that are factorable by a method called the crisscross, which is also my favorite method, or my method of choice, I guess, for all polynomials that are 3 terms. And if you don't want to be bogged down with so many different methods, you can stick with crisscross for all these and it works nice. I do suggest, though, the quick method for problems like this where A is equal to 1. The reason being, you already have half the answer. Any trinomial that is factorable is going to factor to 2 binomials. And you already know that the front 2 terms have to be x and x, because x times x gives you x squared. And it's pretty easy to identify what the back 2 terms are. What you do is you look at what 2 numbers multiply to be c, or positive 6, and add to be negative 5. And the only 2 factors that do so are -2 and -3. If you multiply -2 times -3, you get +6. If you add -2 plus -3, you end up with -5. You can check your answer by multiplying or distributing these through, and you should end up with the original question. We'll look at an example very similar to the last example, where a is equal to 1, it's a trinomial, and there's no GCF. But now I'm going to show you the crisscross method. This is a great method. If you become strong at the crisscross method, you will be able to solve all three-term polynomials, even the ones where a is not 1, which are the much more difficult problems. For the crisscross method, we look at what two factors multiply to be x and list them directly underneath that, which is x times x. We then look at 8 and what two factors multiply to be 8. And there's two different choices. We have 8 times 1, or we also have 4 times 2. The nice thing about the method is we can ignore signs. So I'm going to choose 8 and 1. And so why it gets its name crisscross is I'm going to multiply directly across, or crisscross, and the result will go next to it here, next to it here. Now basically all I have to do to factor this is to figure out what two signs need to be filled in on these two terms in order to end up with the middle term of a -9x. One thing I always focus on is that if this is a plus in the back, they have to be same signs. That'll help you in your decision-making process. And if I add a negative and a negative, I end up with a -9x when I add those two terms. So I fill my signs in directly across, and I have it factored. X minus 8 times x minus 1. Now we will factor another problem that has 3 terms and a is equal to 1. But the difference with this one is there is an additional variable in the back. That is okay as long as it's of this form and you see that it has a y and then a y square attached to the back. All that does is adds a variable to the back two terms in the binomials. So if you liked the quick way, I would definitely suggest that way for the a equals 1 trinomials. But or the crisscross, either one works great. And so I'm going to use the quick way for this example. And I'm going to jump to my answer because I notice there's no GCF in all 3 terms. The front 2 terms have to be x and x since a is 1. In the back 2 terms, what multiplies to be a +4 and also adds to be a +4? The two numbers are a +2, but this is where I put the y and a +2, and this is where I'll also put another y, so that when you multiply them back out. So our final answer can be written as the square of a binomial. You can also do the check to make sure that it works. The next example is also an example of the same form, and I recognize there is not a GCF to pull out. But this is probably the easiest of all examples where we have 3 terms and a is equal to 1 that we've looked at so far. The reason being, it's prime. We cannot factor this problem. So once we recognize that, when I'm looking at the quick way, there is no possible way to find two numbers that multiply to be +11 and add to be -7. The only factors of 11 are 11 and 1, or -1 and -11, which in neither case will add to be -7. Therefore, my answer is prime. The last example we will look at, where we're dealing with a trinomial or three-term polynomial and a is 1, is this given example. Now, I did say a is 1, the reason being you always have to look for the GCF first, and in this case this problem does have a GCF. So we can factor that GCF out, and which is a 2, and multiply times what is left, and we should be left with a p squared minus 7p plus 12. Now, a common mistake is to circle a problem and say, okay, I'm done, I've just factored it. But the directions are always going to say factor completely. Now that is correct, you did just factor this, but to factor it completely, you need to make sure all terms are factored completely. And so we have a factor that's going to follow us along here. It's a 2. But this right here is a trinomial of the forms we've been looking at, where a is 1. And so let's factor that trinomial. It's going to factor down to a binomial times a binomial, and we already know the front two terms. Now all we have to do is identify what multiplies to be 12 and adds to be negative 7. And the two factors that do so are negative 4 and negative 3. The next example is a trinomial or three-term polynomial where a is not equal to 1. There's no GCF, so I'm going to use the crisscross method now to factor this. So underneath the 6x squared, I'm going to try the closest together factors of 3x and 2x. Underneath the 35 or negative 35, I'm going to try the closest together factors of 5 and 7. I will crisscross them. Multiplying 2x times 5 gives me 10x. Multiplying 3x times 7 gives me 21x. Now, is there any way to fill in signs that are opposite, because that's a negative, that when added these two terms, 10x and 21x, I'll end up with a positive 11x? And there is. That's positive and that's negative. Fill my signs in directly across, and it is factored. Now we happen to pick the right setup for this, but say I had the 7 above the 5 in my crisscross, I could try, and if you can't find an example that works out, then you try rearranging or try different factors until you find it. And there's little hints as you go. You can kind of look ahead to figure them out. The next example is the sum of two squares. I know it's the sum of two squares because the front term is y times y, or y squared. It's a plus, and the back term is 5 times 5, or 5 squared. These problems are not factorable over the integers, and we answer as prime. The next example looks very similar to the last example, but remember the golden rule of factoring. You always have to take out the GCF. So in this problem, I will first factor out the 2. Then I'm left with an x squared plus 49. I do now recognize that after factoring out the GCF, I end up with the x squared plus 49, which is the sum of two squares. The sum of two squares is prime and not factorable. Therefore, I have factored it completely, and that is my final answer. Do not make the mistake of writing prime, as you have factored this into two factors, 2 times x squared plus 49. The next example is the difference of two squares. I recognize that there's only two terms, there's no GCF, and that I have a square term in the front, x times x, and a square term in the back, 10 times 10. Therefore, these always factor to a binomial times a binomial. What's being squared in the front goes in the front. The signs are always opposite. What's being squared in the back goes in the back. You can multiply and check your answer. You'll notice that your middle terms will wipe out, leaving you with x squared minus 100. Another thing to notice is these are called binomial conjugates of each other. They're the exact same terms with the middle sign or the back sign switched or opposite. Here's another similar example. I have two terms. I notice the square and I notice the minus. I'm thinking difference of two squares right away. The one thing I do have to do on this one though is I look at the number 32 and I notice, oh, it's not a perfect square, and neither is the number 2. But you do have to remember, always take out the greatest common factor first. If I do so, I factor out that 2 and I'm left with an m squared minus 16. Now m squared minus 16 is the difference of two squares, and I should end up with 2 times m plus 4 times m minus 4, because 4 times 4 is 16. The next few examples, we will look at how to factor the sum and difference of two cubes. In this example, we have the sum of two cubes. The reason being, the front term is a times a times a, and the back term is 2 times 2 times 2, or 2 cubed. Once I recognize this, and there is no GCF in this problem, once I recognize this, I know that the sum of two cubes always factors to a binomial times a trinomial. Now the nice thing about this is that really it doesn't matter if it's a sum of two cubes or a difference of two cubes. If you fill in your signs, and I always do this first, it's always the same sign in the binomial, the next sign is always opposite, the last sign is always plus. So I say same, opposite, always plus. If you can fill that in, you really essentially only have one formula that you have to remember for both of the cubes. Now, when I look at this problem, I look at what goes in the binomial. What's being cubed in the front goes in the front of the binomial. What's being cubed in the back goes in the back of the binomial. Now, how do I fill in the trinomial? Well, take the front term here, stick it in the front, and square it. Take the back term here, take it in the back, and square it. 2 squared is 4. Multiply the two terms out of the binomial together and stick it in the middle, ignoring signs. And I should end up with a 2a. I always write the number first. Here's the difference of two cubes example. There's no GCF, and I recognize that we have p cubed minus 4 cubed, because 4 times 4 times 4 is 64. So essentially it's the same as the last problem. I will fill in my binomial times my trinomial. I'm going to fill my signs in, same, opposite, always plus. What's being cubed in the front goes in the front. What's being cubed in the back goes in the back of the binomial. Take the front term, stick it in the front and square it in the trinomial. Take the back term, stick it in the back and square it. And multiply them together, ignoring signs, and stick them in the middle. The next example appears to be the sum of two cubes, but first we need to factor out the GCF of a 3. 81 is not a perfect cube number, either is 3, so that's kind of a key, but always make sure you remember to look for that GCF. It's easy to forget. So I will factor out the GCF of a 3 times what's left, which is p cubed plus 27. Now I recognize that 27 is a perfect cube number of 3 cubed. And I'll fill in my signs. Same, opposite, always plus. What's being cubed in the front goes in the front. What's being cubed in the back goes in the back of the binomial. Square it, stick it in the front. Square it, stick it in the back. Multiply them together, ignoring signs. Put them in the middle. The next example is a higher order factoring problem where it looks just like the difference two squares, and it is actually, and the reason being that the power is a 4, which is a multiple of 2. So we really do have x squared squared minus 4 squared. So when we factor that, it's plus minus. What's being squared in the front goes in the front. What's being squared in the back goes in the back. But we are not finished yet because the back term is the difference two squares again. The front term is the sum of two squares, which is not factorable over integers. But the back term is the difference two squares, which will end up being x plus 2 times x minus 2. So be careful on higher order ones that you'll have to factor a second step through. One of the factors will actually be factorable themselves.